Hey everyone, and welcome to today's Explainer. If you're building or even just tinkering with modern AI, you already know the deal. The Retrieval-Augmented Generation, or RAG engine, is an absolutely foundational layer. But as we've all seen firsthand, knowing how to string together a basic retrieval script is wildly different from engineering a system that actually works reliably when you scale it up. Honestly, when an LLM hallucinates or gives you a totally subpar answer, the failure usually doesn't lie on the generation model itself. Instead, the problem is hiding deep within the retrieval architecture. Think of it like a massive library search system. If the librarian brings back the wrong books, it doesn't matter how fast you can read them. So today, we're breaking down the source material's comprehensive analysis into the precise mechanics of retrieval. We're going to look under the hood at the core approaches engineers use to fetch data, the critical bottlenecks that cause these systems to just completely break in production, and the exact evaluation metrics you need to score and optimize their performance. So here's our game plan for today. We've got three main sections to tackle. First, we'll look at the core approaches. Second, we'll dive into the common challenges. And finally, Section 3, evaluation metrics. All right, let's get right into it with Section 1, the core approaches. How does a RAG system actually pull the exact right books from our metaphorical library?
Okay, let's dive into this foundational head-to-head competition outlined in the source material: dense versus sparse retrieval. Dense retrieval is all about embeddings and semantic similarity. Basically, this is where you transform your text into high-dimensional vectors. What that does is allow the system to map the actual underlying intent behind a user's query rather than just blindly looking at the surface-level text. It's a real game-changer for complex queries because it genuinely understands context and nuance within that vector space. But on the flip side, we have sparse retrieval. This leans on established algorithms like TF-IDF or BM25 and is all about precise keyword matching. It maps term frequencies. Now sure, sparse retrieval totally sacrifices that deep, nuanced semantic understanding, but it makes up for it in raw computational speed and exact match efficiency. I mean, if a user is searching for a highly specific alphanumeric product code, sparse retrieval is going to outperform dense vector search almost every time by aggressively pinpointing those exact tokens.
The cool thing is, engineers are rarely forced into a strict binary choice here. The source points us directly toward hybrid retrieval. This approach explicitly synthesizes both the dense and sparse methods. By running these approaches in tandem, usually merging and re-ranking the results from both pathways, the system strikes this highly optimized balance. You get the deep semantic understanding you need to parse messy, conversational queries, right alongside the raw speed and precision needed for exact term lookups. Basically, you get the best of both worlds. For modern enterprise apps, hybrid retrieval ensures really accurate context delivery because it actively hedges the weaknesses of one approach against the strengths of the other.
Moving right along to Section 2, common challenges. What exactly happens when this powerful retrieval engine hits a roadblock and starts sputtering in the real world?
It's arguably the most persistent roadblock in modern AI architecture, right? Why does RAG retrieval fail? The generation capabilities of today's language models are literally staggering, but remember, they are completely bottlenecked by the quality of the context they're fed. When a model hallucinates or spits out an answer that sounds great but is factually useless, the breakdown almost always starts right here in the retrieval layer. So, to build resilient AI, we really have to look closely at the specific points of friction that derail the whole pipeline.
The source outlines 4 major bottlenecks that engineers consistently have to navigate. Number 1, ineffective query understanding. Number 2, scalability issues. Number 3, context fragmentation. And number 4, handling multimodal data. Let's walk through these sequentially and see exactly what's going wrong under the hood.
First up, ineffective query understanding. Look, if the system misinterprets the user's intent the second the query is ingested, the entire downstream process is already compromised. The initial vector search goes off in the wrong direction, and you end up returning highly scored but totally irrelevant document chunks. If the query isn't mapped to the right semantic space, you're essentially handing the LLM the wrong briefing materials. Second, we have severe scalability issues. Bootstrapping a prototype with a few thousand documents? Easy. But as your database scales to millions of parameters and embeddings, the computational load becomes absolutely immense. Calculating semantic similarity across large-scale data stores can completely crush your infrastructure, leading to crazy latency or timeouts if your vector indices aren't perfectly optimized.
Our third challenge is context fragmentation, and this usually happens during the chunking phase. If you chunk your documents way too aggressively, the retrieval engine might grab a piece of text that technically matches the keyword, but it's completely stripped of the surrounding context it actually needs to make sense. Missing that contextual tissue severely lowers the final response quality because the LLM just can't see the bigger picture. Finally, handling multimodal data. Modern data pipelines are not just processing neat little rows of text anymore. We're dealing with a messy mix of text, images, audio, the whole shebang. Trying to project text and images into overlapping embedding spaces and then effectively searching across those different formats simultaneously, that creates immense integration complexity.
Let's move to our final section, Section 3, Evaluation Metrics. This is the scoreboard. How do engineers actually measure, grade, and fix these system breakdowns? To actually optimize a RAG system, we need concrete ways to score it. The first absolutely crucial metric is precision. In a retrieval context, precision strictly measures the proportion of retrieved document chunks that are genuinely relevant to what the user asked. You can basically think of precision as your ultimate noise filter. A system with high precision ensures that the prompt window isn't getting cluttered with irrelevant junk, and this is vital. Feeding an LLM too much tangential information doesn't just eat up your expensive token limits, it directly increases the risk of confusing the generator and triggering those hallucinations we all hate.
Precision is great, but it always has to be balanced against our next metric, recall. So the crucial point is, while precision acts as your noise filter, recall serves as your safety net. Recall assesses the proportion of relevant document chunks you successfully retrieved versus the total number of relevant chunks that were actually sitting there available in the database. A system might have perfect precision because it returned exactly one highly accurate chunk, but what if it left a dozen critical pieces of context behind in the database? Well, then its recall is fundamentally broken. Recall ensures no valuable info is left undiscovered. Optimizing RAG is this constant tug-of-war, maximizing your recall without completely destroying your precision.
Now, beyond simply retrieving the right chunks, we have to evaluate the specific order in which they're presented. LLMs inherently suffer from position bias, meaning they pay way more attention to the info placed at the very top of their prompt. So ranking quality is paramount. And this brilliantly illustrates why we use MRR and NDCG. MRR, or mean reciprocal rank, scores the system based purely on the position of your very first relevant document chunk. If your top hit is highly relevant, MRR loves you. NDCG, or normalized discounted cumulative gain, takes a much more comprehensive view. It looks at both the relevance and the specific ranking of all the retrieved documents. By using a logarithmic discount, NDCG heavily penalizes the retrieval engine if the absolute most crucial data is technically retrieved, but buried way down at the bottom of the stack where the LLM is just going to ignore it anyway.
As we wrap up this explainer, I want to leave you with one final provocative thought to chew on. Which retrieval metric matters most for your specific architecture? Think about it. If you were deploying a production system tomorrow, how would you prioritize these trade-offs? Would you optimize heavily for precision, ensuring absolutely zero noise enters your context window? Or would you tune for maximum recall, making sure no stone is ever left unturned? Would you lean on the raw speed of sparse retrieval, the deep understanding of dense embeddings, or bite the bullet and build out a hybrid approach? The answers to these questions are exactly what separate basic AI side projects from truly groundbreaking scalable systems. Thanks so much for hanging out with me today. Keep experimenting, keep building, and I can't wait to explore our next topic with you.